Okay, so now let's get started, and maybe you would like to know who we are and why we're here. So, my name is Damiano Bolzoni. The try was nice anyway, thanks. And he's Christian. I also cannot pronounce his surname. It's 5 years I'm living in the Netherlands. I still cannot make it in Schade.
Yeah, almost.
Yeah, almost, okay. I was once a PhD student. I graduated last year with a thesis about anomaly-based intrusion detection system. I'm now a postdoc, and I have also a spin-off from the university where I did my PhD. So basically this means that I don't do any more fun stuff. It's all about project, money, and supervising other PhD. So that's what I'm doing. I have a PhD basically working in the business of critical infrastructure. So you might wonder why I'm here, because there is no match yet with malware, so it's my hobby so far. Okay, so this is our first attempt to deliver a malware talk. About Christian, is a bachelor student in mechanical engineering. He has been really active in gaming anti-cheating development for years, so yeah, he's also not really, from his bio you would say, why he's also here? Well, he's really talented. He was doing the operating system course under my supervision, and that's how we got in contact. And the guy is really pretty much good at hacking the Windows kernel. So that's basically how we got together. Today, what you're gonna see, well, it's let's walk through it quickly. Well, we will tell something about malware, internals, and we will also have an outlook of the current analysis tools. I think that upstairs you have seen everything, because this year it's all about malware analysis. So each vendor has a malware analysis tool. Then we will talk about our idea, and we will show you what we call the avatar, and then we will have a demo and some conclusion. So, well, you know that malware has become basically a business. People make money out of it. With botnets, for instance, they want to grab financial information about people, username, password that they will be later sold or reused in some ways, and this basically makes it the most urgent problem to address in the cyber world. And it's a big problem because there are a lot of them. So Symantec and their friends are showing every 6 months impressive growing statistics. And this is mainly due to 3 factors, I would say. So the first factor is they use polymorphism. So basically the same sample is just a little bit changed somehow in its content, but not in its functionality. Therefore, you have to develop a new signature for that thing. They use the different packers, so you have every time that you are analyzing a sample, there will be something different in the way it starts. And I would also say that basically malware writers are just better, so they just can kick the ass of the big guys upstairs. So let's say if we look at the way the malware works, in the past, you had this monolithic executable, which means that the malware writer was shipping everything already in the thing you were downloaded or taking from a USB stick or whatever, receiving by email. But this was making it difficult the same way it makes it difficult for normal software, because it's difficult to adapt to OS versionings, because for instance right now Windows 7, if you use the 32 bits, you can do different things from the 64 bits. And it was just easier for an antivirus to spot it, a big thing of 1 megabyte, for instance. There were so much code that could have been detected while running the analysis so the malware writers basically did what the rest of the world was doing. They just switched it to plugins. So right now there are reports that basically rate that 30% of the malware is downloading additional components while you started. So you receive, let's say, a spore, that is responsible to make the malware persistent on your machine. And this spore, which is usually maximum 50 kilobytes, 100 kilobytes in really, really few cases. And so the spore is just, the moment it goes alive, it just pulled down from the network, so from the internet, additional components. So password grabbers, stuff to infect other executables, so to be even more persistent, and so on. So for instance, botnets are this classical example, because you want the botnet to be able to cope with the future, right? So you don't know what you want to do in 3 months. Maybe today you only wanted to sniff password. You only wanted to sniff password, and tomorrow maybe you also want to grab credit card numbers. So you must have a kind of flexible system, the same way as regular software. And let's now have a look at what we have so far to basically defend. So I guess 3 or 4 years ago, we started building, well, they started building dynamic malware analysis tools. So a dynamic malware analysis tools is simply a virtual machine or a bugger system, and actually a very highly instrumented system where you can basically execute the malware in a controlled environment. Whatever the malware will do, it will be logged. So you can see which registry keys have been changed, which file have been created, which files have been altered, whatever, a memory dump of the malware, and so on. So because of course, if we recap the very first slide, we say that we have a lot of samples which are basically the same. They come from the same original sample. And so some researchers have developed what they call the clustering, which is basically a function to say, well, this malware is actually, it belongs to a family of that we very well know the behavior of. Okay? So we're using certain properties, I don't know, the files that are created, the way these files are created, to classify malwares into clusters. There are several of these tools. Some are commercial, like the CW Sandbox, which was before a research project. We have Anubis, Malher, Malnet. They all do kind of the same thing. They are different because one uses a virtual machine, the other one, one uses VMware, the other one uses Kimu, but they all do kind of the same thing. And if we look, so this is for the analysis part. When we want to discover what the malware does, that's what we will use. And then it comes the defensive part, because once you know what the malware does, you also want to stop it. And so apart from the regular signatures, that is basically a flawed model, because one day you will be asked to download maybe 5 gigabytes, or if you're already not downloading today, 5 gigabytes database of signatures, so it's simply going to explode. So they come out with the brilliant idea of creating model-based antivirus software, which is basically using the clustering information to say, well, I don't know exactly this sample, but because it really resembles this very well-known family of malware, I know it's malware. And you use basically the output of the dynamic malware analysis tools to create these models. Now, where are basically, where we come in the picture? So if you look at these DMA tools, they have some problems, as usual. Well, the malware writers are just becoming smarter. So, because malware writers know about these tools, they have implemented several countermeasures that are used to avoid the analysis or to slow down the analysis, because, for instance, the malware runs only if a user is logged in. So, of course, in an automatic process like the one from these tools, there is no user, right? So the malware is simply not starting up. Or, before it activates, it will just wait for a random number of seconds or minutes. So instead of starting right away, it will just freeze and wait 20 minutes, 25 minutes. This is also a problem because if you are receiving something like 10,000 samples per day, you have to run them at the fastest. Yeah, you have to process them really quickly. And if every time you have to wait 20 seconds before you can actually analyze that malware sample, it's just going to take forever. Then there are the very easy checks. So the first one were about virtualization. So the malware checks that it's actually virtualized. Checks for known registry keys, like these latest two checks were the one that were used against Anubis. I don't know if you know about it. It's a research project from the ISEC lab. And also they start because Anubis is, I'm talking about Anubis because it's the one that you very well know the internals being a research project. Anubis was using some fixed IP addresses to connect to the internet. So basically the malware was checking, if my IP address is this one, then I know I'm inside Anubis. So basically the problem here, the problem that you have in this situation is that you don't know the context. The malware, when it's actually executed on a real host, has a different context than the one that you have into the DMA tool. And it's difficult to replicate it beforehand, because it's the usual problem. The attacker just needs to find one weak spot of yours, while you have to prepare for all the possibilities. So if tomorrow they find out a new way to avoid the analysis, we have to start everything from scratch once more. Okay, then there is another problem. If you're using a tool to analyze malware, it means you're usually doing this post-mortem. It means you already detect that something went wrong, and you want to be sure that that little thing is really malware, so you submit the sample and you get a report back. So you cannot really protect your host in real time because the infection has already happened. Right? You can clean up, but maybe this happened actually a week after the malware first went live. And by the way, yes, if you submit a sample, you already suspect it's malware and your antivirus did not detect it. Otherwise, it would have already been killed on the way. So there is no real-time protection with this thing. And you need special instrumentation and a lot of money to buy this instrumentation to run the analysis. Okay? There is just a side note. If you go upstairs, there are a couple of vendors which claim, but I'm pretty much sure that they do that they also run a local analysis. So they have incorporated a kind of dynamic malware analysis tool into their antivirus, so that you run the analysis locally. Problem is, you still have to deploy that solution on each host. And the malware, in theory, could spot it, even if it is a kernel driver, right? So we still have the problem that you find you try to patch, and you still have, they will just need to find out a new way, and you again have to start from scratch. So we were wondering, so we were not really, in the sense, we were not into this business. So we were overlooking at it, and we wonder, is it possible to use this dynamic malware analysis tool on the fly? So let's say without having to run the post-mortem analysis, without having to deploy the software beforehand on the host that I want to monitor. I come from intrusion detection, so my idea is to doing real time, right? In particular, in my original world, in the IDS, they have network operation centers where they do real-time monitoring, or at least they hope they can do real-time monitoring. This basically means, can we create a NOC for malware? Can we have the same thing we have for IDS? So the idea is the following. It's kind of crazy. It came out while working on something that could resemble a honeypot, but is not exactly a honeypot. And we call it Avatar. And you will be, it's clear why it's called the Avatar. You just need to go through the third bullet. So, because we have these additional downloads that have to be performed by malware, you need some extra content providers, right? So it's a web server that has been early compromised, and it's delivering the content. But because from time to time, these servers have to be are switched off, basically, either because they are found to be infected, or because they are found to serve infected content, or just because they were random machine hacked for this purpose, there will be some failed download attempts, okay? So if we can detect one of these attempts, we can supply our own plugins instead of the real one. And so we call these plugins, specifically craft plugins, the red pill. So we give the malware a red pill instead of the original plugin. And when the malware executes that plugin, we do some real-time analysis. So we bring on the host, out of the blue, all the code that we need to run the analysis, or most of it. And we can basically perform an analysis with context, because we know everything about that process. It's running, so we don't need to wait 20 minutes. It's distributed, so with one single point you can control the whole network. And to some extent, you can even, once you are really sure that what you are looking at is malware, you can even ask the red pill to shut it down. Boom. We'll see it later. So it's crazy, but it works. And one could wonder why this unusual combination. Well, the first thing is because I like anomaly-based stuff. So I like the concept that you detect things while they're happening. Like, for instance, you detect the failed download attempts. And then you can wonder, okay, let's just detect the failed download attempts. No, because it wouldn't work. If that would work, then flow-based network intrusion system would have already solved the problems years ago, and they didn't. And we also have to forget about peer-to-peer for a sec to apply this approach, because peer-to-peer basically will screw up flow-based intrusion detection system. So it doesn't work. Don't. There are years and years of research. There are some commercial implementation. They don't work. Well, they work up to a certain point. And then one could wonder, okay, let's do the other way around. Let's analyze every single download performed by my user. So in some countries, this could be illegal, by the way, I guess. In Italy, where I come from, is definitely legal. You will have a lot of problem with trade unions. But let's forget about, for a second, the legal issues, and imagine you are the system network manager of a 10-point-something network. You will never be able to do it manually or even automatically. It's not going to work, because you still have to provide the context. Even if you were able to do it for every single download, you still have to provide the context, and you still have to wait maybe the 20 minutes for the malware to activate. So we just go back to the problem of the usual DMA tools, right? So now Chris takes over. I'm done. I don't do any more technical stuff, so he did the technical stuff. He can tell you how the internals work.
So far we've seen the goals, we've seen the idea of Avatar, but we want to know how it works. I'm going to skip over the three logical components that we need here. First of all, we need something that detects the failed download attempt, which is of course the base of our whole idea. The purpose of this download detection engine is also to verify that what's being downloaded is a binary. And secondly, there's the red pill generator. This can operate in two modes. It can either just send a standalone red pill back without attaching itself to the original egg, which is what was supposed to be downloaded. Or it's going to attach itself to this egg through PE injection. I'll show a bit later how that exactly works. And lastly, there's the malware analysis engine. This is receiving all the data from the red pill, analyzing it, and then sending a command back to the red pill what it should do. Should it terminate the spore? Should it allow execution? So that's the analysis part. We have a nice picture of how it works. the download detection engine and the red pill generator are together on one Linux box. We'll see that again in the live demonstration. So for practical reasons, we've done this in one Linux box, also to show it here. What you won't see is the IP tables rule. So the way we want to analyze all the downloads is having an IP tables rule that's rerouting all the traffic to an Apache module. This Apache module is doing the failed downloads checking if this number of failed download attempts is higher than a certain threshold. When it is, it's going to notify the red pill generator, which will then ship the red pill. And also here's where we do the binary checking, if it is really a binary. Right now we do this through checking the magic numbers, but they could bypass this. I'll mention that as well in the limitations. So the red pill, once it's executed on the host, it's going to try and open its own parent, which is the spore, first with the highest aces mask, which is process all aces. If it doesn't succeed, it's going to try a lower aces, right, until, well, the lowest fails. That doesn't really happen a lot. We've seen in our samples that almost all samples where we were able to open the parent, we opened it with process all aces. In that case, we can either freeze the process and we can terminate it. So actually containing the infection. Once the red pill is executed, it's going to gather as much information as possible from the parent. This information will be used to determine if this spore looks malicious. What I mean by that is, does it look like a program that's allowed to download and execute something? For instance, if the parent, so the spore, doesn't have a window, it's likely that it's not something legal, it's going to download and execute something. So the user probably didn't instruct this process to download and execute. The same with if it does have a window, it could be either very small or it could be off screen. It's all stuff we check, and based on that we say, okay, does it look legal or not? Then all of this information is encrypted and sent back to the malware analysis engine, which can also instruct the red pill to ship the spore back to the malware analysis engine so that it can be analyzed from the start. That's part of the malware analysis engine. This is a real box. It's still under development. It's a real bug. There's no virtualization. So we avoid these countermeasurements against virtualization. It works with a kernel driver. It says here it's difficult to detect. Mostly kernel drivers are easy to detect, but because we own the system, we use rootkit technology to hide ourselves, basically. And also the techniques that are used against Anubis right now, that Damiano mentioned, like it's going to check on which user it's running, it's going to check in which folder. That will never be the same on our malware analysis engine. Or if they know what the serial number of our Windows installation is, we will hook these functions that the malware uses to request, for instance, the serial number, and we'll just spoof it. So we'll always get a different serial number from us. The same with the user and the folders being executed from. And we have ways to interact with, for instance, malware. Let's say that our analysis isn't good enough. We can send it to malware to have, well, a second opinion, basically. Our system has three ways to work in. Transparent mode, semi-transparent, and non-transparent. The first one is transparent mode, is the least intrusive. So once the DDE figures out that there are many failed download attempts, it's going to notify the RPG, which will ship itself back to the host, and only if the file is successfully downloaded. Because in this version, the red pill is attaching itself to the original egg. It's gluing itself. And once the red pill is executed, it's not freezing the parent initially. So it will allow the spore to continue executing. In the next mode, everything is the same except for the last part. Once the red pill executes, it's immediately pausing the spore. And then it's waiting on the verdict from the malware analysis engine to decide if it's going to allow the spore to continue to execute or not. And in the last non-transparent mode, we also straight suspend the spore, but instead of attaching ourselves to the egg, we send a standalone red pill. And once the malware analysis engine says, okay, this program looks legal, it's going to request, the red pill is going to request the original egg from the server and execute it. As with any approach, there are some limitations. The first and most obvious one is we use some static-based heuristics, namely the failed download attempts. What a malware could do is, well, of course, first, if there are no failed download attempts, then it's going to pass through. Unless you put your threshold on 0, well, then you're going to have a lot of legal applications as well that will be intercepted by us. And secondly, the malware could initiate the connections at a very low rate, like every 30 minutes doing one connection request. Then we're probably going to let it pass as well. Well, what the malware could also do is apply some verification, because it's of course going to download something, so it knows what it should expect. If it does some verification and sees that, well, this is not what I'm expecting to download, I'm not going to execute it, then we're not going to do our analysis, but we still stop the infection. And what we've seen from our samples is that none of the malware is actually doing this verification. If they would, it would be harder for them to update. What Damiano mentioned as well, if later they decide they want to seal credit cards instead of passwords, they need to update. Then they would need to update their hashes as well, which is probably something they're not going to do. But like I said, even if they do, we still stop the infection. Yeah? Yeah? Yeah, the question if there's typical executables that the malware is downloading, you mean? Yeah. They're either downloading some executable or a DLL that they're loading. So we need to detect if it's an executable or a DLL, and based on that, ship the correct format back. Does that answer your question? What you also could do is use some steganography. They can hide in JPEG formats. I mentioned that before. We need to do some more checking if it is a binary. There was a talk here on Blackhat today about visualizing a binary. If you've seen that, then this is some technique that we could maybe use. Because then we don't rely on magic numbers anymore, but we basically rely on the entropy of a binary, of a downloaded content to check if it's a binary or if it's an image. And you can quite clearly see what's a binary and what's an image. And the thing I'm the most scared of, they can use create remote thread. So basically what a spore could do is inject a DLL into a legal process, say Internet Explorer or anything else. And then this DLL is going to download and execute the egg. What will happen then is we will intercept this, and our red pill will be executed, but we see Internet Explorer as the parent. So we're going to analyze Internet Explorer and probably allow the execution. But now we don't have a good solution for it. We're working on that. But also from the sample, we haven't seen any spore that's doing this at the moment, because I guess there's no reason to. But if they start doing it, it's a problem. Though it's only possible if they run, if the user runs as administrator. But well, on Windows, mostly people do anyway.
Okay.
So, showdown. Sorry, John.
Okay, so now we hope it works. If it doesn't, we have a movie.
It will work, don't worry.
I've seen so many demo failing there.
First of all, we're not online right now, so we had to create our own egg. Is this thing on? Don't hear myself. It is? Okay. So the egg is just hello world, I'm the originally downloaded content. And I'll first of all show that we have two virtual machines. This is the host, of course. and we have a Linux box. I'll show you here how the red pill generator is working. Right now it's just an executable, of course. It takes the original content here and the name of the resulting file and the DLL that it's going to inject using PE injection. Oh, it just does it, you don't actually see anything. And this inject.exe is a file that gets shipped back to the host on the number of failed download attempts. So what we see here is the server, which is basically the malware analysis engine. The red pill will connect to this server and send information of its parent back. And here we first have a test malware. After that we're going to use some real malware, of course. We don't want to see a test malware. What it just does is create process of probe.exe, and after that continuously run I am running. So you can see how we're pausing and resuming. Because if we check in here, that's what it's going to execute. And if we do that, that's not right. 1 second. Now it is for some reason. It's Windows, who knows. So this is now our probe.exe, and it has sent the information of as the first suspended test malware, and sent the information back to the server, the file name, the path, the window information, but it doesn't have a window, it's a console application, so it failed, and all of the loaded DLLs. Now the server can give an action back, like do we want to resume it, terminate, or terminate and submit, or resume and submit. So let's try resume and submit. So it's going to resume again, and we see here in the target folder that we have the exe again. Let's stop this. I'll show you that it's really the exe. That's the same one again. So now let's try some real malware. After all, it's more interesting anyway. We have a malware from the fraud load family. I don't know if you know it, but it's going to take a few seconds. And then we see it executed something that's PC defender.exe, which is again now attached to our probe. It sent all the information again. So let's now just resume it. And we see here that we still have the original downloaded content. I'm quickly going to show you Wireshark here. I have to scroll up, I guess, to see the GET request. We're not actually online, but we still see this, of course. So here was the GET request for winpc.exe. That was it.
Okay. I can switch back. Okay, so in principle, you've seen it works, and we also have done some testing. So we basically did it in two ways. First, we had to test that the thing, as you can see, as you have seen right now, it actually works. So we took 17 samples from a known data set. Well, known in the sense that you can ask for it. They will tell you, they will ask you, show me your passport and what do you want to do with it, and then they will give you access to this repository. So it's from the people who develop malware. So they have a huge collection of samples that dates back to 2009, and it's basically all samples that have been analyzed by CW Sandbox. And then we also had another data set that we use. So this data set B is malware that we received in a week, a couple of months ago. So it was our regular mailbox. Most antivirus was not detecting it. We collected 30 samples, and then we added 13 good samples. So to test that, how the heuristics are performing. Are we having false positives? So we flag as malware something that is actually not malware. How that would affect the whole process and analysis. So This is also something that you can find in the white paper. So this is the data set, the first data set A, where we all know it's malware and we know they're bad. So these are the families that are, the name of the family comes from the classification that they used to put together the data set. So there are several families. You see also the number of samples. As you can see, there is, and the before last line, there is written a family called nothing found. So basically the CW sandbox says this is not malware, okay? But actually it's doing something. So 3 out of 10 of those samples actually executed our thing, and we could see that they were not good. So there is a kind of mismatching with this. So maybe because the CW sandbox is an automatic process, they miss it. And so if you look at the third column, you basically see how many samples have been basically flagged as anomalous by the download detection engine. So most of the times we miss 1 or 2, so the rate was too low, the failure rate was too low, or there were only a few download attempts, so we didn't detect it. In that case, the malware would have just run regularly. The malware would have infected the machine. And then you have on the very last column basically the numbers for the samples that actually execute our red pill. So once we have found out that we have to ship the red pill, how many of these samples actually executed? So there is only one big failure, which is this kill-off family, for the very simple reason that that family is a kind of, they pretend to be a download accelerator. So they actually leave up to the user to click the button on the downloaded component. So there we can do anything because there is no automation there. And this is the data set B, so where you have the real world, well, also the other one was real malware, but let's say current nowadays malware. So we on first line basically say that out of 30 samples of the bad guys, we detected most of them has malicious with the download detection engine. So 28 were flagged as being malware. So we shipped the red pill. And only one of these 28 did not execute the red pill. Out of these 27, with 13 of them, we could say they are malware just by running the heuristics. So it looks like 50% of the time you can say it's malware just by dumping that information. You don't even have to run the analysis. Then we have that with 2 of them, we did not, the heuristic failed. So the heuristic said, well, it's Goodware. It's okay, you're clean. But actually it wasn't. And so basically they sent, no, there is an error because it should be 11, not 12. So 11 samples have been sent for further analysis. In the other lines basically are the tests with they will basically tell you the false positive rate, because the other lines are about Goodware, real Goodware that we have executed. And so basically in 10 cases out of 30, the DDE component said, well, there is something going on here, I'm going to ship the red pill. And in 6 cases out of 10, the heuristics blocked the process. The heuristic correctly said, okay, this is Goodware, we made a mistake. And in the other case, we just basically shipped the Goodware to the engine. So this shows that it's possible to some degrees to automate the process. And if you really don't want to mess up with the Windows box that you are monitoring, you will just run the transparent mode. So the reason why we have those 3 modes is that you can be paranoid, so you want to intercept everything, or you don't want to block the activity of your users, so you run the transparent mode, or you want a kind of gray approach. Well, not everything, but most of it. So then you have the semi-transparent mode. As already Chris said, basically we found out that there is no sanity check right now. So the malware execute whatever you pass, whatever executable you pass to it right away. So, and also this is true not only for the 2009 samples, but also for the samples that we collected in that week. So we believe that this is because otherwise they would have really serious problem in updating their components, because they would need basically key management or a way to calculate hashes in a nice way, and it's simply not going to work. As I said before, the heuristics are, it seems that the heuristics are good enough to detect, 50%, 50-50, we can already say, well, this is malware. Unless there is that create remote thread issue, which is really scaring us. So most probably in the future we expect this create remote thread to be used for the very simple reason that there are several commercial and research solutions which basically do not check for that, or actually they rely on the fact that they know that Internet Explorer is a safe program. So if the execution takes place as Internet Explorer, they will just let it go. And this is definitely a problem, not only because it's not easy to solve. It's not just something that you can hook in the kernel and do certain stuff. There are ways to go around this. So it's really going to be a problem if they take that way. And as I said, some of these samples did not execute the red pill, so our analysis couldn't go further. So we basically believe that this is not something that you maybe can deploy commercially in your net. I mean that you could do a commercial implementation, but it shows that there is a gap that we have to fill, basically. So this is a proof of concept. Maybe next year we will have a better solution, or we will narrow down certain things and we will decide only to consider certain cases which are the ones that are happening more often. We don't need any software at the end host. This is an advantage because you need to keep it updated, and I guess the system administrator knows how this is painful, how much this is painful. So you just do it on the fly. Whatever you need for the analysis, most of it is deployed on the fly, real time. You can have the single point has the malware analysis engine. That's the only one where you have to run the updates, but it's one point. We offload the heavy computations because when I mentioned before that this solution that basically which runs the analysis locally, they will basically take a lot of CPU time. Yes, we can offload on GPUs now. Still, your host is basically used as a dynamic malware analysis tool. So you might don't want this, right? So we offload all the computation somewhere else. And as we show in the demo, you can, if you're really paranoid, you can even press the red button and basically kill the malware right away, or suspend it, or whatever. This depends on the OS because Windows 7 64 bits has some differences with Windows 7 32, for instance. You cannot do the same thing. Nice that Microsoft implemented these functionalities, but it's possible. So we know that you can get around these analyses. It's clear. But if they decide, for instance, it's very back, so let's not jump to that slide. But if they would like to implement cryptography, if they would like to implement steganography, if they would like to implement hashing, keying, or whatever, this will just make the spreading of the infection much slower. Because then you need the real infrastructure behind to manage the keys or manage the hash. They will have to reveal themselves because there must be a single point that is always active that the malware can use as an oracle. Is this component good? Can I use it? Right? So in that moment, either they reveal themselves or you will find out what is the key or the hash or whatever. We are planning to publicly release the code of the red pill. So this is the URL. I know that in the presentation that the Blackhat has put on the CD there is not this information, but we will update it. We will send a new presentation to the Blackhat staff so that they can put it online, so you can play with it at your own risk. And we're done. So now we can take questions. Sorry? Yeah.
Thank you. Question. So this will work with the malware goes out and grabs more stuff. It doesn't work in cases where malware already has everything to do with the platform.
So the question was if this approach works only if the malware is downloading some extra components, or if it's going to work also if the malware is basically a monolithic executable. Well, in principle, no, it cannot work if the malware is not pulling down extra components, because the idea is we stop something that we inject into the malware. So we need really this phase in which we get into. That's why also the presentation is called Goodware drugs, because it's like giving it a medicine. You need this phase.
How do you detect that, you know, the executable, the failed executable downloads?
So the question is how we detect the failed download attempts. So far it's a very naive approach. I would say that that's the weakest point because it's anomaly based. And so we just basically, there are some algorithms that, so in this case is the threshold walking algorithm that we adapt a little bit. And you basically have a rate of successful and failed attempts for that particular host or for that particular network that you can set. And then you basically can set a threshold and say, if it fails more than this number, provided they have seen this amount of failed downloads, then you are going to basically shift into operational mode and you will ship the red pill. So that's the weakest point right now, because it's not a silver bullet. We know that. So the worst case is the malware gets in, but it would have gotten in anyway because your antivirus has failed. Otherwise, the antivirus would have stopped it. And yeah, so sorry guys, but we couldn't make it. There is that.
I'm curious. So it relies on failed downloads to detect its behavior. Have you thought of maybe intentionally failing potentially suspicious-looking downloads, and then seeing if it retries that download again, like a legitimate application would, or if it tries a different site then immediately?
So with the dataset B, we have tried to basically fake the downloads. So that's why 10 samples have been flagged as malicious. I would say that it depends on the working mode, because as I said, if you are paranoid, you will send right away the red pill, right? Whatever. Oh, there is a failed download. Yeah, here is the red pill. If you have this transparent mode, you basically wait for the file to be pulled down, so to actually find this file, so it may take another 10 attempts, but you know that then you're going to glue the red pill to it, and you will run the analysis. So yes, these are all weak points, and that's why I'm saying this is kind of proof of concept, and definitely you can do better. We just need some time, because this idea came out of the blue in March. So we want to make it work better, definitely. There was another question? Yes?
Yeah, one thing I'm not clear, you're saying that the failed download detection is the weak point.
Yeah.
On one hand. On the other hand, the numbers you showed here show that most of these failed downloads were eventually detected as real malware. So it does seem to give a pretty good chance.
Yeah, but it's anyway a controlled setup. So because I come from the anomaly-based detection world, I can assure you it's the weakest point. So I would not trust it. It's the only so far it's the only thing we have found out that you can do, because apart from installing something on the machine, so provided that you don't want to install anything on the end host because you don't want to maintain it, you don't want to update it, and because you just don't want that shit on your machine, that seems to be the only way. So we can either refine it. The approach works, as I said in one of the very first slides, the approach works because there is this combination of two things. The idea came out because we were working on a honeypot that is not a real honeypot, that is monitoring everything, not waiting for something, and use again a kind of double approach, where you use the failed download as a kind of first line alert, and then you have something more on the honeypot that will tell you this is something really going wrong. So here is the same thing. You have a first line of alerting, which is the failed download rate, and then you have something else that will confirm or not your suspiciousness. So I would say that if you just take one of the two, that it doesn't work. Because otherwise, if you take the flow-based, that's the technical name for that thing, flow-based analysis, they would already have solved it 10 years ago. Arbor is selling this solution for already 10 years, and I think we still have malware out there, right? So it doesn't work. The approach has to be smarter. I don't know if this is smart enough, but it's an initial step.
And then I was also just wondering about performance, like how much latency does it add, like how much computational power do you need, say for supporting 1,000 hosts, or do you have any idea of those numbers?
Okay, so no, we have not definitely tested with 1,000 hosts. Sorry, yes. So the question is if we have any statistics about the workload that is required by this approach to work properly. So no, we don't have numbers with many hosts. I think that the latency when you are on the host to dump the information is basically not zero, but close to it, right? Right, Chris? It's just you dump information from the executable, and that's kind of straightforward. We have also some encryption because we don't want sensitive information to go over the network like this. So maybe that's the one that requires most computation. But because the actual analysis does not take place on the monitored host, but somewhere else, the only problem could be that if you really want to be paranoid, it's going to cost you a lot of time because you have to run first the malware, and then decide if the heuristic failed, because they failed, they are called heuristic for something, because you hope it's going to fit. But if it doesn't fit, then you have to go for the further analysis. And the further analysis is expensive in terms of times, because you have to wait for the malware to show up as malware or to be confirmed it's clean. The only good thing is that you can, the same way as like cloud antivirus, you can maybe have 3 or 4 different engines that you use at the same time, because you have the copy here in your hand of the original spore, so they're supposed to be malware, and you just send it out, and the first one who says something, okay, you take it for granted. It's malware, okay, I will switch it off. Yet, let's say that even if you are not paranoid and you cannot run the risk of switching off the malware right away on the host, you can still have the information that something went really wrong. So you might allow the execution of the end host to continue. You have the copy, you will run some extra analysis, it will take you 1 day, and after 1 day you know that the host is compromised. For some use cases, this is enough, because they want to know that the machine has been compromised as soon as possible. They don't care if some information, of course you want the information to stay inside your network, but they will not die for this, right? So it's all about your business case, I would say. Any other? Yeah.
Have you, in your research, seen any malware tunneling its communication over DNS requests?
Okay, so the question is if we have seen malware tunneling, so basically using side channels to communicate outside the world with something that we cannot control. As I think we forgot to say this, but so far we are monitoring the HTTP traffic, right? So in theory, this approach can work for any protocol. You just have to decide that you are gonna monitor a certain port. Yes, not in this project, but yes, we have seen. Yeah, in general, yes, we have seen there is some malware that is tailored, really tailored. I mean, we are talking about government agencies. They receive some tailored malware for a certain user, and that malware is going to use some side channels to cover channels to communicate with the mother. So yes, they do exist, but so far we monitor HTTP. In theory, it's possible to do whatever you want. So actually, I think on DNS it would work even better because the DNS requests are so simple to, let's say, validate. So if all of a sudden you see something that you cannot validate, you are kind of sure that something weird is going on. But unfortunately, I would say if it's not DNS, they will use something else. So, I mean, the range of possibilities is quite wide. Yes? Sorry, didn't get the question.
What's your mechanism for delivering the red pill?
Oh, okay. So the question is, what is the mechanism to deliver the red pill? So the Apache module is sitting in the middle. It's like a mod proxy. Okay, it's a modification or addition, whatever you want to call it, to mod proxy. So when you start the download, when the file, depending on the working mode, blah 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 blah, we verify basically. We start verifying what is being pulled down. And at that moment we say, okay, it's an executable, so we send ours instead of this one.
So how much disruption does that cause to the target?
So far we haven't, the question is if there is any disruption for the target. So this is a good question. So far we haven't seen this, but we do expect some disruption, for instance, in the case that the download is big. And you have also to take into account that, for instance, if the file is a zipped archive, for instance, that could be a problem. There are self-extracting, sorry, not zip archive, but self-extracting archive. That could be a problem because they also have redundancy check for, so they are expecting a file of size X, and now I'm shipping a file of size A. So that could be a problem, yes. So there are some mechanisms that we have to put into force to be sure or to work better, because otherwise in that case we just would have to let it go. Okay, I have this guy and then I'll come back to you.
There's a question about in terms of how you do it. Based on what you said, you download, you actually replace the file. Have you ever encountered something like the downloader actually infects what it downloads first and injects another downloader there? So if you do put your blue red pill there, you actually be the one downloading it now once it starts the process.
So the question is that if...
Then how do you deal with that?
So the question is if that by having a double download, right?
It's like a double,
Yeah,
like
having a double download, what would the approach would...
because you can see this thing in the older malware that does it is probably, you could say like code red, I think. Some of it will infect some of the PE files, and the PE files actually becomes the downloader for other components. But this one is more like you do it in the downloader form.
So it wouldn't work in the sense that we would see that the actual downloader is Mr. X, let's say Internet Explorer. So because of the heuristics that we have right now, in this version we would fail. So we would say it's clean. To solve the create remote thread problem, we are thinking about basically, I mean, there are some ways you can fix, because if to do that thing, yeah, either you basically know or are able to analyze what's inside the memory of the process, for instance, but that's going to cost you a lot of time, so could be infeasible, and the result is not guaranteed. So that would be another way of circumventing this approach. Yes? Okay. Yeah. So I will just repeat the question and then let Chris. Yeah, I told you I'm senior. I don't do that stuff any longer. So the question is, how does it work when we append the red pill at the end of the file that is actually downloaded?
So in short, it's done through PE injection. I don't know if you know this. If I have to explain it, then I guess I have to use this board, if that's okay. Well, I can do it easily right here. If you come a bit closer, you can see it.
Remember that the guy is an engineer, so. It was a good command. I'm not an engineer. I'm a computer scientist. That's the problem.
So if you have the binary of the egg, here's the board PE. Somewhere in the somewhere in the PE, this original entry point is listed. And what we do is we, in the PE, replace the original entry point with our entry point. Here we have kind of, this is not working. So our loader stub is here, which is written in assembly, is completely relocatable, so it doesn't depend on where it is. Then we point the entry point here to our entry point, so let's say new entry point. And here we append our DLL.
So that's why, for instance, you basically broke totally the CRC.
Yeah. So we appended DLL because we don't want to write or complete analysis in relocatable code. That would be very annoying. So just this loader stub is relocatable. What it does is takes this part. It knows exactly where it is because here it's written start probe or something, and here's end probe. So between these offsets, it's taking this binary data, putting it in a file, and then basically calling load library, which will execute our probe DLL. And then when the malware analysis engine says, okay, this is clean, so resume execution, it's just going to execute that original entry point again.
So only if it's clean, you
Yeah.
go back to the...
Exactly.
It's like, you're like much like a virus.
Yes.
Yeah.
True.
Yeah, we are a virus.
But you have to fight them. It's fight fire with fire, right?
Exactly.
That's another way to circumvent it. Like the downloader knows the heuristic places where the entry point normally lies. Because that's, if you are normally, let's say, normal P file, normally lie about 1,000 hex after the section, first section. So you can always, after you download, replace it back and then launch. So you already
That's true. But actually, it's not always 1,000 behind the.
No, if you use if you compile it in Visual Studio, normally that's the range. You get that
Yeah.
as an entry point.
Yeah, but then you can still say that we fall back by using the. We just ship the red pill.
Yeah.
And then the red pill will take care of taking again the original file in case it's clean and do its job. So, yeah. In a
So
gray
this is-
area, but we
Yeah.
can still make it.
But this is basically only handy if the spore has some kind of relation with the downloaded egg. So it's maybe sharing a pipe or something. Then in this case, this relationship is still maintained. If we would send our own standalone exe, there would be no relationship anymore. So that's why we also opted for this solution in some cases.
In my opinion, we would really like to see is that, okay, we gave away the idea, and somebody comes and say, well, here is the way to make it work really in the real world. It would be nice. So that's why we hope that we have feedback on the way it works, because we would like to have more ideas to include more counter techniques.
Yeah, especially also on the remote DLL injection. If you have any ideas how to detect that post-mortem, then please talk to us.
I'm sorry.
No.
Because I'm more familiar with P as well. How many times in this type of mode the failure points in terms of it attaching itself to the code. Because like sometimes most Ps are a little bit compacted. So when you do add the code, it kind of destroys all the file alignment and the section alignment. But when you execute, actually it goes haywire.
But we are at the end, so we basically actually appending. So
Yeah, but you still need to rearrange all the. For example, you attach yourself in the resource section, right? Then you have to rearrange the resource section, and then if you add an even or add number of bytes there, you have to rearrange the file alignment or the section alignment. If you don't do that, you're gonna go screw up. When you jump in, actually, Windows will detect that this is an executable and probably fail.
I think you should see our code and how we add this code section.
Okay.
Because I don't think we have to do any realignment, or
You
at least I didn't do it and it still works. So
Okay, so you probably
Maybe we were lucky. Maybe we just got lucky.
Yeah, because some packers who, some of the files, let's say the alignments are 100 only.
yeah,
And if you extend it a little bit more, the line should be, a valid alignment should be 1,000. But if those things are not correct, then the code won't be loaded. And of course, it will constitute error message that says this is not valid.
I think maybe we never ran into this. So it's yeah. So I'm not saying it's not happening or you're wrong. Just yeah. Maybe we haven't seen it. Yes. So far with all the samples that we had, it always worked and.
but we will have the source online, so you can have a look how we do it and comment on it.
There was yeah. It was first.
In the cases where you see that it's trying to download a DLL, and you go ahead and replace, just put in your red pill as the DLL and don't go into it. At what point do you get execution there? When they load the library?
Yeah, exactly.
Just your DLL and every team just takes over.
Yes.
I can catch up.
Okay. So yeah, I think we can conclude because there are only some survivors left. So I hope you will enjoy the pool now. Now I hope I see you there. Thanks.